Hey, so in the last video we defined resonance, and we basically said that resonance is looking at different depictions of the same molecule, and these depictions, these resonance forms, differed from one another only by the locations of certain electrons. And we called these electrons delocalized electrons, meaning that they weren't stuck, they weren't localized on an atom or a bond. They could move around. So when going from one resonance form to another, we keep the connectivity of the molecule the same. We just move a couple of electrons here and there. And then we went a little bit further and we said that resonance forms have different weights or significance representing the molecule as a whole. And these differences in significance are based on the stability of each resonance structure. And then I gave you 3 rules to abide by when looking at the relative significance of one resonance form to another. And the first rule was open shell versus closed shell. Open shell. Closed shell. And so now I'm going to do this example. So this is acetone. And to create a resonance form, we can take the electrons from the pi bond and we can move it up. And what this does is that those 2 electrons originally belonged in the bond. They originally belonged to both oxygen and the middle carbon. But now they only belong to the oxygen. And this means that our carbon just lost 2 electrons. It only has 3 bonds surrounding it, and therefore it only has 6 electrons, meaning that it's not open shell. Or, I mean, it's not closed shell. Now, just because we have a resonance form that is not closed shell, it doesn't mean it's not a valid resonance structure. In fact, this resonance structure is important when it comes to acetone's reactivity. However, having an open shell in your resonance form makes it significantly less stable than an all closed shell resonance form. So we can conclude that this molecule on the left has more significance. That's not a fun green. Has more significance when representing acetone than the one on the right. And this is, so the open shell versus closed shell is the first thing you should look for because the difference in stability is so great. Open shell is not very stable at all, and closed shell is very stable. So those are the big factors when considering stability. The second thing you should look at is formal charge, or formal charges, I should say. And what the trend is ultimately is that the fewer the number of formal charges, the more stable that resonance form is, and the more significant it is when representing the molecule as a whole. So let's look at this structure. And this is just some random structure. And now what we can do is we can move these electrons to form a double bond with carbon, and since we don't want carbon to have 5 bonds total, we will move these electrons in the pi bond as to a lone pair in nitrogen, and what we get is this structure. And if we okay, so in both resonance forms, you can double check, but just take my word for it, that all the atoms are full octet, meaning they're both closed shell. So we can ignore the first rule. We can go to the second rule, which is formal charge. So now the first resonance form doesn't have any formal charges. However, when moving these electrons, we create two formal charges on the molecule. One being a positive charge on the oxygen, and the other being a negative charge on the nitrogen. So we have two formal charges on the one on the right and none on the initial one. And we have to remember that formal charges are a sign of instability. Formal charges mean that the atom doesn't have the same electron density surrounding it as it's normally associated with, and it wants to have that same electron density, but because it's stable that way, but since it doesn't, it loses a little stability. So this one on the right is not as stable as the one on the left, and therefore the one on the left is a more significant resonance form. It embodies the molecule as a whole more completely than the one on the right, because it has a fewer number of formal charges. The final rule to go by, I guess, was electronegativity. Electronegativity. And so when looking at electronegativity, we're basically looking at which atoms have the formal charges. And so when going from one resonance form to another, we may keep all atoms closed shell, and we may keep the number of formal charges the same. However, the placement of those formal charges is important, because some atoms handle formal charges better than others. So case in point, we're going to look at this guy again. Only we are going to add a base. So let's add sodium hydroxide, and a base will take away our most acidic proton, which is this guy, and that bond that was originally between the nitrogen and the hydrogen will become a lone pair on nitrogen. And now we can draw a resonance form between this new guy, so I'm going to draw him again. Oops. Okay. So this is what we end up with after deprotonating. Now we can draw a resonance form where we take the lone pair from the nitrogen and we form a double bond with this carbon, and then we take the electrons in the pi bond, in the double bond between oxygen and carbon, and we move it up. And because it's good practice, I'll draw my lone pairs. And that'll ultimately get us to this guy. Negative, double bond, lone pair. Okay, so here are our two resonance forms, and so between the two resonance form, all atoms are closed shell, and we each only have, they each only have one negative formal charge. So now we have to decide which atom can handle this negative formal charge better. And that's a little difficult to figure out, but we can go back to our trends in electronegativity. So we know that oxygen is more electronegative than nitrogen, which means it has a stronger affinity for electrons. It likes having electrons. So basically, oxygen can handle this negative charge better than our nitrogen. And because it can handle it better, it's more stable with the negative charge on the oxygen. Yeah, so that was a good example. I'm going to do a counter example too, so I'm going to erase this, and now I'm going to draw oops, let me go through this one real quick. So we can, let's say we have this molecule, and we can draw a resonance form where this pi bond becomes a lone pair, and then these lone pairs become a pi bond. And that'll get us to this guy. So I figured out the formal charge on the nitrogen on the left, and it was a positive formal charge. And now in this new resonance form, that positive formal charge is shifted to the oxygen, and now this is the exact opposite. So nitrogen, well, oxygen is more electronegative than nitrogen, which means nitrogen is more electropositive than oxygen, which means it can handle that positive formal charge better and is ultimately more stable than the resonance form with the positive oxygen. So this one is the more significant resonance form, meaning that the molecule as a whole will have this guy as a higher characteristic than the one on the right. So that's how you determine the stability between resonance forms. You first look at open shell versus closed shell, you then look at the number of formal charges, and then you look at where the formal charges are. Yeah, so that's how you compare resonance forms. Next time we'll look at how to draw resonance. We'll figure out actually where I'm getting these arrows from and stuff like that. So, yep, thanks.